All right, geometry. Hey, welcome back to proofs. So 2.5, we're going to start right in with some geometric proofs. We're going to prove some segment relationships. So we're just going to be proving some things about lines today. So we're gonna learn a couple of postulates. Some of these are kind of ridiculous, actually, to be honest, but that's okay. Like this first one, 2.8 that you see here. This one's actually not used, you know, that much for proofs. It's just kind of it's an important idea, like if you were to actually try to prove something with somebody. But the ruler postulate just says, basically, know that when you line up a ruler, one endpoint should be at 0 and the other one will give you the length. That's kind of a no-brainer, but actually there are people who struggle with measurement, like and lining up their rulers. So some people like to start at 1, for instance, instead of 0. But I believe I've seen enough from you guys to know that that you're comfortable making a measurement. But the ruler postulate basically just gives us a postulate to a commonality of how to measure. So we always line something up with 0, and then we can figure out the length of it and all be on the same page. So don't worry about that one too much. But the segment addition postulate, okay, this one's an important one. If A, B, and C are collinear, then point B is between point A and C only if AB, which is this distance right here, right? AB plus BC is equal to the total AC. That's called the segment addition postulate, and it does come in handy when we're doing some proofs. So let's start right in on example 1. So again, we just learned segment addition postulate. We're probably going to be using it in example 1. In fact, I see that they actually even give it to you there. So in example 1, you're kind of, when they start you guys off with these proofs, they actually set the proof up for you pretty nicely, and then your job basically is just fill in some of the missing pieces. So the very first thing says in this proof, basically they give us that AB is congruent to BD. Sorry, AC is congruent to BD. So this distance here is congruent to this distance here. Okay, that is our given. Okay. In order for us to get to a place where we're talking about equals versus congruence, we basically just have to convert that right away. And so oftentimes, you guys, you are going to see this come into play. Like almost I'm not going to say every proof, but a lot of proofs we're going to do this step that we're going to do here first. The step is, if we want to go from congruence to equality, to equals, then what we have to do is we basically, the reason that I can say that if two things are congruent, they're also equal, is because of the definition of congruence. And you can actually just write it just like that. I know it's kind of silly, but this is part of what proofs are, what's involved with proofs. Is if we want to talk about something being equal versus congruent, we have to bring in our definition of congruence. Okay, so I can rewrite that with an equal sign now that I have that. Okay, and notice what I'm trying to prove here, you guys. I'm trying to prove that AB is congruent to CD, so that this guy and this guy are congruent to each other. So one of the things that I want to highlight with proofs is, because this happens often, is that if we're starting with AC and BD and we're ending with AB and CD, we somehow have to bring these two pieces into our problem because we don't start with them, right? So part of segment addition is, let's bring in these pieces. Okay, so what we're going to do is we're going to look at our picture here and look at what we see, and we can now say, all right, well, AC is made up of two parts, right? AB and BC. So I can say, okay, AB plus BC must equal that total distance AC. And that's the reason that I know that or can say that is the segment addition postulate. Okay, so here I'm going to fill in a couple of blanks. This would be AC. And if we do the same thing over here, maybe I'll change colors. BC and CD make up BD, right? The distance BD. Both of those things can be done based on segment addition postulate. And the reason that I'm doing it is because I want an AB and a CD in my answer. So that's why they're bringing those in right now. Okay, because we're trying to get to that point. All right, so now what I can do is I can essentially say that AB plus BC equals BC plus CD because notice that AC and BD are equal. Okay, so if these two things are equal, I can say that the things that they equal are also equal. So I know that's confusing language, but these two things have to be the same as well, right? So I basically eliminated these because I already know they're equal. And now I can say, okay, AB plus BC has to equal BC plus CD. All right, so pause the video there if you need to rewatch that and look at that again or just study it a little bit. The reason that I can do this is this is a substitution. Okay, so I'm substituting these guys for AC and these guys for BD. Okay, substituted them. All right, now that I did that, notice here we have this common thing in both pieces, which is convenient. So think of algebra, right? If I have like 2x plus 2 equals, I don't know, 2 plus 3x or something like that. If these two things are the same, right, like BC is the same in here, if I go to get rid of it, if I subtract 2 from this side and subtract 2 from this side, both of them go away. Right, so I can subtract the BC from both sides using my subtraction property. It's the same subtraction property that I use in algebra. Okay, so now what's left once I get rid of the BC from both sides is just AB equals CD. All right, and I can rewrite it this way because of substitution. Okay, it's always a substitution when you're simplifying a problem like this. So we just simplified using a substitution. And now to go from here to congruent again, because I got to go from equal now to congruent, I can do that and make that a congruent sign by the definition of congruence. Whew, that's a lot for our first kind of real geometric proof. But this is the kind of thing that you guys are going to be doing eventually on your own. They're going to give you a lot of support at the beginning, so don't let it scare you. It'll be a lot of fill in the blanks, but you will do some of these on your own very soon, maybe even this lesson. Anyway, let's keep going. The reflexive property basically just states that, that this, like you could say AB is congruent to AB or BC is congruent to BC, and you'll see why this is handy here when we do this one. So it says this is used when we need to use the same line segment to make statements about equality. So in this case, we could say, BC is congruent to itself when we're trying to prove that AC and BD are the same. So we could, like, if we have BC in both of our statements, BC and BC, this guy is congruent to itself, so we can kind of eliminate it, all right, using the reflexive property, and then we can just say, since these are equal to each other, then I know that this distance, if this is the same, has to be the same as this distance as long as A, B, and C, D are the same. Anyway, this is a reflexive property. It seems a little bit silly, but sometimes we just have to show that the same piece is equal to itself. And it's kind of weird, but that's just the thing that we need to make a logical argument. The symmetric property of congruence states that if AB is congruent to CD, then CD is also congruent to AB. Notice that these things can switch back and forth, right? Which can come in handy occasionally if we want to just change the order of something. We can't just change the order without a reason. We have to use the symmetric property to change the order. And then the transitive property, this is the one where we can eliminate the middle guy, right? So if AB is congruent to CD and CD is congruent to EF, I can just cut out CD and say, okay, AB must be congruent to EF. All right, so let's move on to example 3. It's a carpenter problem, kind of a real world problem, where you cut 2x4 boards to a desired length. He then uses that board to make a pattern to cut the second board congruent to the first, and then similarly uses the second board to cut a third board, and the third board to cut a fourth. Then it says prove that the last board cut in the measure has the same measure as the first. So, and then they tell you how to label the boards. Okay, so if we drew a picture here, first board is, we'll draw a picture, we'll label it KL. Okay, the second, he uses that as a pattern. The second board then is MN, third board PQ, and fourth board RS. So let's go ahead and do a proof of this. So notice, you guys, if we're trying to prove, let's do the proof. So here we go. So KL is congruent to MN. Okay, and we know that MN is congruent to PQ, PQ is congruent to RS, we drew a picture. Okay, so what I need to do is I need to get RS and KL in there by themselves. So all of this stuff needs to get eliminated. Okay, so that's what I'm going to attempt to do. That's what the proof will do, is try to eliminate all that stuff, and then we have an equal sign here instead of a congruent sign, so I'm going to have to get that congruent sign converted. Okay, so I kind of get my steps, kind of see where I'm going. Okay, so if I'm trying to eliminate things, let's see if I can do that using my transitive property. So since KL is congruent to MN and MN is congruent to PQ, I could say that line KL is congruent to line PQ. I cut out these guys using the transitive property. Okay, now here I want to pause, okay? KL I have here, I'm trying to get an RS in there, and I don't want anything else in there. Okay, right now there's a PQ. Okay, let's see, now that I have this PQ here, I know that PQ is congruent to RS. So I could say, since KL is congruent to PQ, and I've stated that, now what I could say is I could say, okay, KL is also congruent to RS. Okay, and the reason that I can do that is also transitive property, right? Because of this guy right here. Okay, so transitive property allows me to do that. Okay, now I'm trying to get the RS first because that's what I want to prove, right? So what I need to do is I need to flip the order of this thing. So to do that, okay, I can flip that order. The reason that I can flip that order is from the symmetric property, which we already talked about. Symmetric property. Then I need to go from congruent to equals. That's my last step. The way that I go from congruent to equals is always my definition of congruence. All right, so that's example 3's proof. We will do some of these together in class, so don't stress too much. But I just wanted to give you that last little piece, and I will see you guys in class next time. Don't forget to fill out your notes, and feel free to start on the homework.